All right, so today's lecture is looking at the stages of visualization, at kinds of symbols, things that are sensory or you have to think about them, arbitrary symbols, data characteristics. And data characteristics is something that's not really in the textbook. And so today's lecture notes will be useful to keep around for the class. It talks about how we're going to describe the data sets and think about them, visualization goals, and then kind of a completely different section on props, right? And so this is kind of how do you put things in the visualization that show you what's going on. But as usual, we're going to start with looking at some examples. All right, so here we're going to do what has kind of come to be called, look at something that's come to be called ensemble visualization, right? And so the idea is you have a simulation, you run the simulation with different sets of parameters or maybe with different initial conditions, and you then want to compare the differences between these different ensemble runs to see which are similar and where the differences are. In this case, they're trying 4 different vortex core identification algorithms to kind of say, okay, of these algorithms, which ones catch the vortex cores we're looking for, how similar are they, and so it's basically a comparison technique among algorithms. So this is the same simulation data, the kind of flow past the block, with 4 different kind of algorithms for deciding where vortices are. So a vortex is, there's different definitions. One is basically the center of a tornado, as you can think of a vortex. And so this, they have different criteria. Lambda 2 is one of them for understanding is it a vortex core or not. So this is seeing how these things relate to just the Lambda 2 criterion, how they work with flows, with steady flow, with unsteady flow. And so here they're basically showing, using color as a way to nominally show different data sets and then showing all 4 of them on top of each other. And they're so thin that there's not a lot of problem with occlusion. And so it works well just to show that all 4 sets of them on top of each other. All right. Here's a technique that deals with the problem of if you take an isosurface, we're going to talk about this in basically volume display. An isosurface is, for example, everywhere in this room where the temperature is exactly 22 degrees Celsius. Right? It's the surface between higher and lower than 22 degrees. If you take CAT scans of a particular mechanical part, of a person, or a CT scan versus an MR scan, and you do an isosurface that shows you the thing in one image, it's actually not going to maybe exactly match the other image. Maybe there's a little bit different settings on the machine, maybe there's a little bit of drift, or between CT and MRI, there's very big differences in the levels, right? And so this is saying, well, if you just take the same ISO value on the left, on the bottom right is what you get from the second data set. But what they do instead is try all the different ISO value levels and look for the one that's got the most similarity in the visual representation to the one on the left. And so it's basically saying, okay, find me whichever one is most like the one I have here, so I can compare kind of apples to apples these 2 scans, rather than having to go chase around on the left and then chase around on the right, back and forth and back and forth. So it's kind of an automated assistant to help you understand what's going on in the one on the right. And the third is a custom design that was for the visualization design contest a few years ago, I think 2011, where they were looking at how do we decide which way we should access the person's tumor in their head so that we avoid very important tissues and other areas. I clicked on the wrong screen. So which way we can go in, right? And they came up with a new technique.
We employ an intuitively perceivable and well-known natural phenomenon that is usually called God rays, or kripa.
And yes, this is the portal voice that they use for the voiceover, right? This is like, for me, if I had to do a voiceover in Chinese, this is the only way it would work, right? Is just feed it into the speaker and it would go. So that was a very clever use of this.
In nature, bright light sources form crepuscular rays in dusty air. They are influenced by the shape of trees, or by the frame of a window, or other obstacles. We think of a tumor as an omnidirectional volumetric light source in an isotropic scattering medium. Vulnerable structures act as completely opaque or semi-transparent obstacles that block the virtual light which is emitted by the target structure. Our interactive visualization system provides a 3D representation for a good overview over all access paths. We call the safety information for each path, path safety. In order to convey the safety information also in 2D, we additionally calculate the available leeway for all possible entrance areas and display them with color-coded lines of different thickness. We call this information area safety. In the following, we present several use cases for this approach. First, an artificial patient. 2D slices lack the depth information. In this image, the red area shows an artificial tumor. It is difficult to determine the overall extent of a safe area. To tackle this problem, we propose to encode the given algorithm for every safe access area with color and with different line widths of a projected geometry. As already mentioned, we call this information area safety. This geometric information is derived from the path safety volumes. We show also the computed path safety volumes in 2D. In this scene, we show only paths which reach at least 80% of the segmented tumor areas. Because of the computation in 3D, we can display arbitrary multiplanar reconstructions on the fly. In 3D, a simple one-dimensional transfer function is sufficient to control the visualization of the path safety volumes. This example shows only...
All right, so here we see kind of the benefit and the deficit of showing things as kind of direct volume rendering with opacity, right? You can see everything, everywhere there's an area, but understanding the shape of that region and where it extends into the screen is going to be challenging, right? So there's a fundamental trade-off, occlusion versus confusion. This particular choice was a more confusing but more inclusive way of displaying the data. The 2D slices is completely not confusing, but you only get to see one slice at a time. So these are kind of looking at these trade-offs. But the idea here is to make the thing you want to look at glow through the other things, then you can look at the actual kind of trace rays behind to see what's going on. So it's a way of computing the thing that you wanted to see directly and then rendering that thing as part of the visualization and then doing it in context. All right. So, administrative. So my office hours, I post on the webpage, but also want to let you know they're Mondays from 10 to 11 and Thursdays from 9 to 10. I tried to pick a Monday, Tuesday, and a Thursday not at the same time to miss your constraints. If there's something that we need to talk about and you can't come to one of those, send me an email. We can try to schedule a time. But these times I'll be in my office ready to talk about homework questions, design ideas, data sets, how did I calculate your grade on this particular thing, whatever you need to talk about, I can come and talk about that. The WordPress site's up and running, and so some users have already registered for that site, which is good. Go ahead and upload your private posts by next Thursday. Then I'll make them all public, and then you can do comments on other people's posts by the following Monday. And that's how the period we're going to go through the first 5 homeworks is you'll upload them privately, I'll post them, you all will be commenting on each other's, and in fact this year you're just going to comment on a subset of the other ones. Last year I had everybody comment on everybody's, and that was a lot of time commenting, and so you'll just be commenting on the nearest ones to yours. I'll be grading independently and writing my own comments that will be private, and then will show up publicly at the end when I've graded them. But we'll basically post the results privately, look at them, comment on them, and then next week we'll be starting again. And so it's a fairly complicated homework pipeline. Again, it was 12 years in the making to try to optimize it for getting it to do all the things we want to do, but not have to do things we don't want to do. But yeah, it'll be exciting. Okay, and so. In Colin Ware's book, he talks about the foundation for science of data visualization. And he talks about the different advantages of visualization. And so what were some of the advantages that he talked about in that section? And a lot of them are illustrated. He used this to illustrate them.
I think one of the things he talked about in that figure was that you can immediately see some artifacts in the data.
Uh-huh. if I can spell. Indeed, so there is this weird kind of wavy artifact that was in there, and they're trying to understand what the heck is going on with that. And that was, well, the boat that was taking the measurements was rocking a little bit from side to side, and so things got a little taller, a little shorter, a little taller, a little shorter. Useful to know about your data. Wasn't actually in the thing you cared about, but still useful things to know. So yeah, you can see things you didn't expect in your data. What were the benefits you talked about?
Also, the visualization can help us to the hypothesis formation.
Exactly. Yep. Right. So, first is, what the heck is going on here? Well, let me think about what could be causing this visual feature. Yep. So, right. It helps you think about new questions you can ask about your data, new analysis you might perform. Yep.
It allows you to see trends in the data that you might not have noticed by just kind of looking at it. Like in this three-dimensional space, you can see the lines of the indents. That's one of the things he talked about was the line.
Exactly. So he talked about the emergent properties, right?
Yeah.
There's dots in here, and so you could have seen the dots in any slice you look through, but the fact that they form little lines that are not aligned with the X or Y axes, I mean, why should they be? It's which way your boat was driving. And they're, kind of what's causing that? No hypothesis, what's going on with that data? Exactly, yep. All right, so the other thing you mentioned was it lets you see details in context, right? So you can see, the dots are kind of like that. You say, okay, near the trench over there, is there more going on than far away from the trench? Let me see the large-scale features, the small-scale features, how they relate to each other. And of course, it lets you see huge amounts of data. So instead of peeping through the numbers or peeking through statistics, you can see this. And so I was trying to think about how to succinctly put this several months ago as we were writing a grant proposal. And it occurred to me that like using statistics to look at your data is like playing the game 20 questions, right? What's the median value of my data set? Is it larger or smaller than 5? Okay. Are there any values that are lower than 7, right? You're kind of trying to play 20 questions to come at the thing that you want. And if you know, the exact thing you want, then that works very well. But if you're trying to determine what's going on in your data, the visualization helps you know which questions to ask so you can more rapidly get at the science that you're trying to do. Okay. So visualization occurs kind of in a framework, and it occurs in stages, right? And so first you go to the lab and you collect your data, or you run your simulation to get some data, or you do a literature survey and you pull your data out of it. Then you transform it into a form you can get into your program, right? And we talk about into the form best suited to show what you're trying to understand about the data. Then you run the visualization algorithm on some graphics hardware, and then you look at it, and then you change some parameters, and you go back to the visualizing, change some parameters, and that loop happens many, many, many times. And then you may come up with a new hypothesis and say, okay, well, let me look at this in a different space and see if I can see things more clearly in the Fourier domain, right? If I'm looking for patterns over time, maybe transform the Fourier domain. And then you say, oh, wait a minute, is there something wrong with my equipment? I'm seeing some feature I don't expect. Let me go back to the lab and try another experiment run. Or what if I change this, technique, parameter on the input device? How would that go? And then, preferably, once you've come up with a new technique and a design, you're saying, okay, is it really showing me what I think it's showing me? Let me do this on a technique, on some data where I know the answer, and see if indeed it matches up, with this technique. And so we're going to be talking on the visualization interaction stages, but keep in mind that this is going to, when you're working with a scientist, sometimes the answer will be, oh, I have to go collect a new data set because of something you asked. Or let me give you another data set that I hadn't thought about before because I can ask a new question that I hadn't asked before. All right. So sensory versus arbitrary symbols, right? So this is kind of one of the fundamental distribution of way that we're going to draw things in this class. Sensory is something you can see and you can understand without any training. It comes naturally. You've kind of been doing it all your lives, all of your life. It matches the way we're wired, right? There's no, it kind of has a perceptual basis. You can do this without having to read the instruction manual. Arbitrary symbols are kind of arbitrary, right? You have to learn them, right? And so, the word dog, right? All of these things mean dog. I'm trusting the translator that I got is from. For some of these, I have no idea if that's what, it means dog, and some of you are laughing, so maybe it doesn't. And so, but the point is, you'd have to do it. There's no way to know this unless somebody told you how this was going, right? And so, this is, the two transways. And of course, actual visualizations may be a mixture of these two, but think about some of these are just you see, you know when you see it, and some of you have to think about it. So when would you choose sensory representation? So what are the benefits of these, right? The good news is they can be understood without training, right? We take advantage of the perception of the 3D world around us. And a good visualization, good mapping to a visualization channel can be taken out of context and still be understood. It can have poor instructions or legends and still be understood, so it can be a very good way to display things. But perceptual illusions show that sometimes these can actually be a problem. Because even though I've instructed you to tell me whether these lines are parallel or not, and you know in your brain that the answer is going to be that these lines are parallel, visually they say no, there's no way you say these lines are parallel, right? And this is the one that I showed before, where if you kind of remove the cross lines and believe that I didn't do some magic trickery in the behind the scenes, they're there, and you put them back, and they will go right back to being when they were, right? And so they're a very powerful way to do this, but you need to be careful not to fall into some pits. And I'll describe 5 or 10 of those pits as we go through today in the next few lectures. So the arbitrary representations, they're basically formally very powerful. So if you imagine mathematical notation, you can very succinctly describe a very complicated relationship in a way that kind of tells you what's going on. You can rapidly change them, right? So you can say, well, now temperature is mapped to the color red. Now height is mapped to the color red. Now pressure is mapped to the color red, and so you can do the same task over and over again, and you can very rapidly switch between things as opposed to having to remember which is which. It's hard to learn, easy to forget, and it can vary with culture and application, right? And so I is different things to different mathematical symbols, and colors mean different things in different cultures, and so that can be an issue to deal with. All right, so another way to think about visualization is what happens in the early part of the visual system. This is what I talked about as the pre-attentive section, where everything happens in parallel. And then what happens in the later parts of the visual system, where I'm looking around trying to understand what's going on, right? So I can quickly detect that there are faces in this room, but if I want to know who you are, I have to actually look at your individual face to find, is there a particular person in this room? That I'm doing at a higher level of processing. And it turns out, as we'll see, that what you're trying to do in stage 2 can affect how things are happening in stage 1, right? So if you're looking for dark objects, if you're looking for a dark object in a scene, you can tune perception to more quickly be able to pick those up. If you're looking for white rabbits, then you can more tune to quickly be able to pick those things up. And so we should decide which techniques are best suited for the parallel processing and map those, to the most important tasks to those channels. Okay, so going back a little bit to what I talked about in the last lecture is asking what's a good visualization, right? And I said it wasn't whatever's the coolest visualization. Let's put some meat on what it means, right? So understanding means making a model that captures the essence of a system, right? I want to understand this. I want to understand what's going on in the essence. I want to have a simplified model. So a model is an abstraction with the important things in and the unimportant things out, right? And so it turns out there's no way to have a model that includes everything. It's just the original data set, which really means I don't want the extraneous stuff. I want the important stuff. Well, different visualizations give you different level of detail. They show and hide different things, and so they support different abstractions, right? So if I'm looking for areas where it's the highest, that will hide the areas that are lowest. If I'm looking for high frequency areas, that's a very different I can support that with lighting, but not so well with color, and we'll see this as we go through the class. So good visualizations are those that are useful to aid understanding, not just realistic, right? And so one way to think about this is if I ask you, what color is a carbon atom? And I make you answer the question.
We don't know.
Right? One is we don't know.
It probably doesn't have a color because a single atom isn't going to reflect light.
Yeah,
So
exactly. There is no color.
The answer is no.
You're right. Right? There is no color to a carbon atom because it's smaller than the wavelength of any light we would scatter on, so it scatters all light equally. So formally there is no color, so we had to make something up. But there is actually an answer to this question.
Black.
We represent
Black.
it as black.
Why is it black?
Because the chemists.
Because the
that
chemists
way.
color it black, exactly right. So it's an arbitrary representation, and if you draw a molecule, you better draw the carbon atoms black.
And most things we see that are carbon are
Or
black,
black,
so.
yeah. Or sometimes they make them green, but yeah. So, so basically,
It's
yeah.
oxygen or
So,
nitrogen.
you know, so there are the reasons to make it black, and the reason is because everybody understands that it's black, not because that's the realistic representation of that. Right? Okay. And we'll see later as we look at the kind of way we can color things. Sometimes adding realistic rendering to it, to a scene, can make it harder to interpret the scene. Right? Some things are hard to figure out what you're seeing. You know, if you fill the room with fog, that would be a problem for seeing the things that are beyond the fog, but very helpful for hiding the things that are behind and showing things that are in front. Right? And so be thinking about, what is it that I wanted to show, and let me map that to something it shows, and what is it I didn't care about, and I don't worry that I have to hide something. So the obvious questions are, what are the relevant characteristics for each task, right? And what techniques show them best? And so we're going to have a zoo lecture of here's all the techniques and what they show for all the for 2D scalar fields, for 3D scalar fields, and so forth. And this turns out to depend both on the data characteristics and on the question that the user has in mind. And so today we're going to look at the data characteristics, and then as we go on, we'll talk about which ones are better for which colors. All right. So now we're going to classify things according to data characteristics. And why would we want to do this? And the answer is because there is no kind of one winner-take-all visualization technique. Right? You can't say what's the best 2D scalar field visualization technique. Well, depends on the questions. So this helps you know which techniques to try. If you have a good technique that works on one thing, it helps you know to predict what other things it might be good for that have similar goals, that have similar data characteristics. And some tools only work with some formats. And so that'll help us understand, if we wanted to do interval mapping, we shouldn't even use these tools over here. All right, and again, you'll probably want to print this. So I'm going to adopt this taxonomy in these terms for the course. It's somewhat arbitrary, but at least it'll be consistent, right? So when we talk to each other in critiques, when we talk to each other about why we pick design choices, we're going to use this particular taxonomy of words to describe this. Dimensionality is the thing I'll talk about first. What's the dimensionality of the data? What are the category of each value or field in the data? What's the structure of the sampling in the data? And then, of course, other, which is the things that don't fit in the first three. So dimensionality is a very overloaded term in visualization, right? So it can mean the kind of dimensionality of each data field, right? So in other words, I've got some data. It might be at a point. It might be at a line, which is 1D, or a 1D curve. It might be a 2 surface that I've collected the data in, or it might be a volume that I've collected the data in. Right? So this is the dimensionality of the field that I've collected the data from, right? And so we're going to use that to mean the field. Then also the space that the field is embedded in, all right? So what's that mean? So, for example, I might collect data on a 2D plane in this room, but it's a 3D space that I'm collecting the data from, right? And so, when we saw that simulation of the airflow in the wing there, that's a 2D, slice, but it's from a 3D field that it was doing, right? So there's a question about the data field that I sampled, the space the fields are embedded in, and so I'm going to call 2D or 3D plus time. I'm not going to call 2D plus time 3D. I'm going to call it 2D plus time because there's differences between time. Now you may, as a visualization technique, say, well, I'm going to collapse that into a 3D space for the purposes of visualization, and that's sometimes a good choice. But let's think about originally what is the field that these are in. All right. And then there's the data type in each field, right? So the data you collect along this line in this 3D space may be a scalar field, meaning it's got one value at every location in space. It may be a vector field, meaning it's got a direction and magnitude at every location in space. Or it may be a tensor field, which I'll have a whole lecture on, that basically talks about how vectors transform into vectors in that space, all right? And so sometimes you'll be reading a paper and they'll talk about the dimensionality, they use it to mean any of these terms, right? And there's also the space that you use to visualize the data in, right? Okay, and so that's distinct from the space that the data was collected in. You could take, your 2D sample and draw it as, 2D plus time as a 3D output space, right? Where you remap the dimensions on the way in. So the question is what the dimension of the output space. And people will confuse these sometimes, or have different meanings for those in papers, but we'll stick with these for the purpose of the class. All right, so let's look at some of these. So the other thing to consider is that the thing may be projected on a 2D screen. So formally all of these are 2D because they're on a 2D screen, but this is a 3D display, right? It's intended to show you a 3D shape, the fact that it's projected onto a 2D screen, okay, I get that, but the main point is you're trying to show the thing in a 3D space. Whereas the one on the, the lower right is a 2D display. You might say 2.5D because there's layers, but that's a 2D display. All right. So in the upper right, we've got basically a scan by an atomic force microscope that measured the height of the surface, and it measured the sideways stiffness, or in other words, the stickiness, the adhesion of this, the kind of lateral force you go move things. And it's moving around this carbon nanotube that you can see got wave back and forth, all right? So this sampling is 2D, right? It's in a 3 space. The height is a little bit interesting to think about, right? Because it's a 2D sampling of a scalar field, right? It's not a 3D sampling. It's you're measuring in 2 dimensions a thing that is a height. It happens to be in the 3rd dimension. And then you're also measuring a second data field, which is deflection lateral. So it's 2 2D scalar fields in 2D. We were measuring the surface of this object in the AFM. We weren't measuring the volume around it. And it's drawn in 3D. Okay? So we took one of those data sets, height, and we mapped it to a deformation. So we've got a 3D model, and then we mapped the other one to color. All right. And so in the lower left, we've got a 3D vector field. So we've got flow again around this blunt fin. Right? The blunt fin is going to show up all over the place in this class. So the air is flowing in here. There's an airfoil wing here, and it's blowing around. It's causing a little turbulence here. And so this is a 3D vector field. Every point in space has got a direction and a magnitude. And it's rendered in 3D. It's extracted from 3D. So the data space is in 3D, the field is 3D, and the rendering is 3D. All those things match. All right, so this is somebody's brain with their head with a tumor inside. And this is kind of looking at a surface of the skin, a surface of the brain, a surface of the tumor. So this is 2D isosurfaces of a 3D scalar field in 3D. Okay, so there was a 3D scalar field. That was the kind of volumetric data that had density at every location. And what we're rendering are 2D surfaces in 3D. Right? So if you're an ant and you walked around on the surface, it'd be locally flat. It'd be just living in a 2D world. All right. So in the lower right, as I talked about this, we've got the simulation again over the blunt fin. We've got 2D vector fields, tensor fields, and scalar fields. The space that the fields are embedded in is 3D. In other words, there's a 3D simulation, but we sampled for this part in 2D, and then we're rendering it in 2D. Okay? And so we'll talk about the type, the dimensionality of the data field, of the space, the type of each data, and then the space used to visualize the data. So the dimensionality is very overloaded, but there you have it. So some visualization techniques will work for scalar fields, color, for example. Others will work for tensor fields, glyphs, ellipses, and so forth. And so we'll see all these different groupings of techniques as they apply to these different kinds of fields through the course.
Just by looking at that, the last one, you can't say whether it's a 3D, it's a 2D mapping taken from 3D, right? It has to always be mentioned.
That's right.
Yeah,
You
so
couldn't just by looking at those glyphs know if that was in fact a 2D simulation space.
Or just a piece of modern art.
Right.
Yeah.
And so that's why I like to, and it's actually useful, it's kind of a little bit, sounds pedantic, but useful to think about these steps, because then it breaks you free to say, oh, well, the height here is shown as height, but it doesn't have to be. Right? It could be shown as contours, could be shown as colors, it could be shown as any of the other techniques we can do in 2D. Height is the kind of natural one to do, but is that the best for the question that I want to ask? Yeah. Yeah. All right. So then there's the category. If there's a scalar field, scalar fields have categories, right? And so now we've had types, which is kind of scalar, vector, tensor, and category. So category, I talked about this a little bit last time, but nominal is, like the continents. There's no particular ordering to them, they're just names. People's names are this way, company names, so forth. There's no order relationship. An ordinal is less than holds, right? And so pizza is this way, rental cars are this way. You don't know how much bigger in volume one is than the other, but kind of the subcompact is smaller than the compact, is smaller than the mid-range is smaller than the full size, right? Then there's interval, which is where you can actually do interval measurements. Right? This one, the difference between these two data values is the same as the difference between these two data values, or these two data values, where this one is greater than the difference between those two, so you can measure intervals on your data. And then ratio is there's some absolute zero, right? Twice as much as. Your bank account balance is a very good example of this. You care very much if it's above zero or below zero, and so does the bank, right? Because fees start kicking in.
Do you really mean ratio? Don't you mean, I mean, you really mean that just there's a zero, right?
Yep.
I mean, it's not a quotient.
Yep, so Rachel Brady and I had this philosophical argument every time I do this, and she takes that position, and I'm perfectly fine if you want to think about this as, yeah, it's interval with a zero in it. Because all that ever matters in this class is like, does it have an important zero, right? Because that'll say, do I pick a technique that's got a clear gray thing in the middle or not? So I'm fine if you don't worry about the fact that division is not necessarily the thing we care about, but the fact that there is zero. But it turns out that having a zero lets you do ratios, and so that's the name I give it. So yeah, you could say interval with or without kind of a 0 point, but if you say interval and you don't tell me which, I'm going to think it's that, and if you say ratio, then I'll know. So again, it's not the perfect nomenclature maybe, but we'll go with it for the purposes of describing things in the class. All right. Then there's the structure of the sampling grid, right? And so this is these data points are sampled either in a 1D or 0D or in 2D or 3D. And the question is it a square grid, or cubic grid, which is kind of a square or cubic grid, rectilinear, which is square or cubic, but can be stretched differently in the different three axes, right? So it's like kind of a square but longer this way. Curvilinear is it still has the same structure, but you can curve around the space that it's going in, right? So this is one where we've curved a curvilinear grid around the blunt fin, where there's kind of smaller elements here near the fin and the bigger ones outside, and they move to follow kind of further and further distance away from the fin. So you get higher detail near where you care about and less detail further away. And so this is a curvilinear rate structured grid, right? This is an unstructured grid, which basically says we've got a bunch of points and we've tied them together somehow, and you're not going to be able to figure out, given one, where the next one is, except by traversing the data structure and seeing who it's connected to, right? So here, you can have implicit coordinates for all this data, right? So you can say, here's the grid, and here's my block of data. With this, you have to say, well, here's the data, and here's where it's sampled, here's the data, here's where it's sampled, here's the data, here's where it's sampled, and you kind of don't know anything about how do you get to the neighbors without doing some graph search. This turned out to be mostly important in understanding, can my visualization tool show this, right? And usually when you care the most about this is my visualization tool can only do some subset of a rectilinear grid, so I need to resample my data onto that grid, and how do I deal with this? But other techniques do in fact work on unstructured grids. I'm starting to put more unstructured grids into pair view, so this is becoming a little bit less of an issue, but it's just something to think about in terms of the grid. This won't typically affect the visualization design as much as it affects how you're going to do the workflow pipeline to get it into your tool and display it. All right, so other characteristics that turn out to be important. There's continuous versus discrete in two different ways. One is in sampling of the space, right? So we're almost always here going to have discrete sampling of the space. Either you've got a certain number of stations you've measured things at, or you've got a certain number of locations you've simulated things at, right? When I was working with the applied mathematicians, and they gave me the answer to the equation of how does this sphere move as this kind of thing circle around in space, I'm like, okay, what's your sampling? And they're like, no, here's the equation. And I'm like, yeah, but they're like, this is the equation for all space and time of how every point in space moves around this. I was like, wow. So that was a continuous. Okay, it's in a computer. But the equation is continuous. You can analyze it anywhere. So that's continuous in space. Rarely do we get that. Usually it's discrete. And the fact that it's discrete can cause errors and missing data. And we need to think about, what is the sampling size and how is that going to impact what we're going to display. There's also values within the sample, right? So you get an 8-bit camera, or a 12-bit camera, or a 16-bit camera. What does that mean? That means it only can have, at every pixel, some number of values. If it's an 8-bit value, you can have 256 values. If it's a 12-bit value, you can have 4,000 values. So it's got a higher dynamic range. So the maximum brightness to the kind of minimum perceptible difference is different for those cases, right? And again, almost always, on simulations, we usually have continuous to the level of floating point precision in these simulations, but experimental data is almost always some discrete value, right? So how many bits do I have? And this can be an issue because, for example, if you show kind of isocontours At some values, you'll see these plateaus, right? Where it's like, why is there a plateau? Well, because the camera can only measure 1s here, and they can only measure 2s here, and so it's got flat regions. Not because the brightness was flat, but because the camera itself could only capture a certain number of levels. And so you can see some artifacts in the display because of that.
Nyquist theorem.
Nyquist theorem's coming next, yeah, so there's rapid spatial changes in the data. So this is asking, okay, if you look at kind of the data set, is it smoothly varying everywhere, or are there ever sudden changes, right? Or are there high frequency oscillations? And so Nyquist was a guy who talked about how you sample this so you make sure you're capturing all the important frequencies and you're not mapping high frequencies you didn't capture down to other frequencies. The only thing we care about in this class is some visualization techniques can show you rapidly changing things, highly detailed things, and some can't, right? And so really what you're thinking about is, do I need to show something highly detailed? If so, then I'm going to have to map it to one of these techniques that can show high detail. Are there missing values, right? This is something that makes me crazy as a computer scientist. No, we just have all the answers everywhere. No, that day lightning struck that sensor and it was dead and we don't have any data there. What do you want to do about it, right? And usually what you want to do is ask the scientist, well, what do you want to do about it? Because sometimes they'll be like the kind of the consumer grade camera, right? What they do is they basically, some pixels in your camera are dead. They don't even tell you that. They just interpolate right across it, right? And so that part of your imagery, you don't even have the resolution you think you had, but you didn't pay for a pro camera, so too bad. In the pro cameras, if you get the raw format, it'll actually have a mask for, here's the pixels in the camera that are bad, and so if you're going to do some photo editing on it, you can know. And so in that case, you're actually leaving out that value, and so showing especially this is missing, right? Scientists may want to see, no, I don't know what the value is here. I'm not going to interpolate it across. I'm going to show you that I can't see what's here. Maybe I don't draw the surface there. Maybe it's a special color. But think about when you're looking at the data set, are there missing values? And then ask, what should we do kind of about those missing values? And then special values, right? So 0 is pretty important for height above sea level if you want to know, am I going to get wet as I walk around this area, right? 0 is really important for the bank account balance. And so think about, okay, how do I want to show this particular value? They're not always at 0, right? So there might be the tree line, they might be the snow line, they might be different things that aren't at 0. Are there special values, and how do we want to highlight those in a particular way? Okay, so here's an example of some data characteristics. So this is a magnetic resonance image of a brain. We're seeing here a 2D slice through that MRI, right? So that's a 2D, display of a 2D sampling from a 3D scalar field. Drawn, brighter means more dense. Then we've got these contours of an algorithm that's used to find vesselness, right? How much is this like a blood vessel? And so these are contours, these are 2D scalar field, 2D surfaces extracted from an algorithm from the original data, and they're colored nominally, right? So this is just one set of blood vessels, another set of blood vessels, a third set of blood vessels colored nominally, right? And so they're, they don't really have data on these surfaces. The surfaces themselves are, this is the edge boundary thing. There's no scalar field on there, but it is a 2D surface that is the isosurface in 3D. All right, and so both of these are presumably derived from the same 3D rectilinear ratio scalar field, right? So what's that mean? So rectilinear means it turns out that when you do an MR scan, it's very rarely the case that they kind of, the cross-plane resolution is as high as the in-plane resolution. They usually take bigger steps there. So it's rectilinear, it's square in XY, it's stretched in Z. It's a scalar field, it's just the density, and it's ratio. There is a kind of a 0 that matters, right? This is kind of how much density there is. And you can have twice as much density or 3 times as much density in different regions. Okay. Here's another example, and I'll let you kind of tell me about. So the upper left is a scanning electron micrograph of a surface, an SEM image. And then lower left is, and that's mapped to brightness here for display purposes. In the lower left is a data set that's an atomic force microscope scan, so it's kind of a topographical height scan of that same surface. And shown here with kind of brighter and more white is, kind of hotter is higher. And so on the right is a combination view of these 2 data sets in the same thing. So somebody describe for me kind of what that the type and the so forth, the upper left data set is.
2D mapping taken from a 3D.
Right? It's a 2D field taken from 2D. It's on the surface of the object, and it's what kind of field? It's a scalar, vector, tensor.
Scale.
Scalar, yeah. And what kind of scalar? Nominal, ordinal, interval, ratio. I guess it's required so you know how SEM works. So it's the number of backscattered X-rays, which is ratio.
Ratio.
Yeah, there can be 0 backscattered X-rays in place, and it kind of matters. There can never be negative backscattered X-rays from place. All right, and so tell me about the lower left.
You said that was atomic force microscopy?
Mm-hmm.
So that's 2D data
Mm-hmm.
obtained by a 2D method, right?
Mm-hmm.
And that would be ratio, again, I believe, 'cause it's based on the intensity. So if there's no forces,
It's
it's
based on the height.
based on, oh, it's based on the height, okay.
Still ratio.
I think it's still a ratio,
Yeah, it turns out it's interval,
yeah. Okay.
right? So there is no sea level, there is no absolute center of the earth 0 for it. So you could assign, for example, the bottom of that trench as being the sea level, and then it would turn it into ratio.
Okay.
But if you shifted the whole thing down and scanned it again, you get the same data. If you shift the whole thing up and scan it again, you get the same data. So good. Right,
Well, so the zero is just relative to wherever the stylus is in its.
You get zero
Spirit
kind of relative
movement.
to how far the motors drove the thing down before it started scanning. Yes,
Yeah.
it's not relevant to the data. It's some coordinate system in the device. It has a 0, but the science doesn't care about that, right? They care about kind of relative heights. of
Oh, so
places.
so the interval is it may have a 0, but you don't care.
Yeah. So in that case, your view of the ratio is more correct. Did the scientists care about the 0 or not? If they don't care, it's interval, because we don't need to show it to them. If they do care, then it's kind of, we need to show it to them.
Right, because it's not strictly differential, it's just, I mean, it is over a range, and a linear range,
Yep.
right, I presume, and, yeah, okay.
Yep, all right. And so then the display on the right is a 3D display of these two 2D data sets, one projected onto the other one lying in the same place. All right. Okay, so visualization problems versus data types, right? So medical data is, very commonly 2D scalar square or 3D scalar rectilinear, right? It's, kind of CAT scans, MR scans, X-rays, so forth, images. Scientific data is usually 2 or 3 or 3D, can be structured or unstructured, kind of often a scalar or vector. And information visualization is kind of n-dimensional, who knows what kind of structure it is, it's usually unstructured and sometimes not even spatial. Right? Okay, so now we've talked about data characteristics, now let's talk some about goals and how they're going to impact things. So if you think about things, there's kind of high-level goals that the scientist has in mind, understand how earthquakes work, right? Middle-level tasks, understand how waves propagate through different media. And then atomic actions, like understand what the kind of magnitude of the kind of vibrations are here in the relative phase is. So kind of high level, mid-level, and task level. So you should determine your tasks, kind of the middle level, before deciding what representation you want to do for visualization. Right? You shouldn't say, oh good, I'm going to get to use volume rendering in this thing. Well, let's find out what the task is first and see. Now, the tasks sometimes are informal or implicitly defined, right? Sometimes you have to dig to ask exactly what they want, and sometimes you kind of have to figure out what the task would be to meet that goal. And something to remember is you may not get it all in one display, right? If you want to do 2 or 3 different tasks, you may need 2 or 3 different representations, hopefully in the same place so that you can kind of compare them directly, but maybe even different visualizations side by side or so forth. All right. So some visualization goals. One that I've talked about is debugging, right? I want to do quality control and see if the boat was rocking in my simulation, see if my sensor was even turned on, see if there was lots of noise in the samples that I was taking, see if the data format even makes sense that I read it in the right way. So you shouldn't think this, again, as unimportant, because about half the time we get data from scientists, there's something strange in there that they didn't expect that kind of caused them to upside, one image may be upside down with respect to the other. You do statistics, the statistics don't make any sense, or worse, they do make sense, but they weren't correct. But if you look at the things together, you can see what's going on. So exploration is basically saying, I want to understand what's going on here, right? And this is the most vague goal, right? It's like, let me explore, let me see what's going on in the data. Let me form a hypothesis. This is, you want to increase scientific productivity because you're coming up with new hypotheses to look at, and you want to make the invisible visible, right? I want to see inside somebody, and I normally can't. I want to see what the electric field looks like, and I don't have my eyes can't see the electric field, and so forth. The presentation is basically saying, okay, now I understand something, and I want to tell a story, right? And so the thing I've been passing around here is I want to tell a story of some thing. I want to show you the highlights of the important things and convince you that this is the right thing. So it's a visual medium of comparison. Okay. And so those are the goals, and within each goal there can be several tasks. All right. So with an exploration, for example, that goal, there's kind of a spectrum here from very specialized. I want to identify, distinguish objects, right? So this might be saying, okay, I want to identify the kidney, or identify the liver. I want to measure the volume of the kidney, or very specialized goals. Categorize things. Compare values. Where's the highest areas in this watershed? Where are the lowest values? How are they compared to each other? And kind of at the more general is I want to see patterns or structure. Right? Where are there clusters in this data of things that are near by each other that are high valued? Do these two data sets tend to vary in the same way, always high when it is high, always low when it is low, or kind of contrary-wise? And then the most general one was just, let me look at this and see what the heck is going on here. And so, what's going on here, we'll kind of have to punt and say, well, we're going to show it to you a bunch of different ways and see if you see anything. But if there are more specific goals, then we can help you pick, which might be the best way to display them. So a presentation task is basically saying, okay, I want to show you significant features and give you an understanding of how I think that they relate to each other. I want to convince you that my hypothesis is correct, compel you to believe it with this, or I want to attract interest, right? So whenever we submit a grant proposal, we want a wonderful kind of color graphic of our data that people look at and say, wow, this is really cool. Or if we want to go to the general public and give a talk, here's some interesting visually thing to look at that you would like draw you in, draw your interest into the talk, and go forward. All right, so one of these, an example here, one of my favorite examples of this, as I'm passing around, is Edward Tufte's display of Menard's eloquent picture of the losses that Napoleon's army suffered as he assaulted Moscow, right? And so the width of this is the number of men in the army at the time. The coordinates is where they were on the Earth. And the kind of going forwards towards Moscow is gray, and then coming back from Moscow is black. On the bottom, he's drawn the temperature graph to show you kind of what happened as the temperature went down and down. There's topological features here, so a lot of people when they cross the river, right? And so you can see time is marked along the axis. So this has got time, motion, quantity, temperature, all these things mapped together in one. And basically his message is the saying for the Princess Bride, which is never get involved in a major land war in Asia, right? Or more specifically, more generally, he meant don't, war is bad, right? So this is giving you the message, war is really bad, you don't want to be doing this. Now,
Don't fight the Russians in the winter.
Don't fight the Russians in the winter is more specific, yes. And so, it's a very compelling graphic. I don't know how to generalize this, right, to a whole theory of graphics. I've seen it used for wines going from different countries to different places. It works very well for that. So if you've got a similar thing, this is a very good kind of motif to pick up on and draw. All right. So in summary, there's data characteristics and there's goals. And basically for each data characteristic, you want to think, okay, for this technique, is it going to work well because the dimensions and data types are supported well, or is it not going to work well? For each visualization, what's the best space to map this into to show what I want to do? And then if there's rapid changes or missing values, I need to take special care. If there's zeros, I need to take special care to show those in an effective, kind of intentional way. For visualization goals, you want to think of what they're trying to solve before you pick how you're going to show it to them. and you want to consider which tasks are to be achieved and techniques suited for each. And then the final consideration is, does this work? And that happens at a very simple level when you look at the visualization the first time and go, wow, I can't see anything, or yes, I think I can see things. But at a deeper level with the user study that understands, okay, is this really effective at answering the technique, or do I just like it because I made it up, right? And that's kind of the place that I end up falling into myself. Oh, of course you can see. I love to see talks that say, oh, you can see this and this. And I'm like, really? If I knew that, maybe I could see that in there. But testing it against kind of a user that's not you on data sets that you know the answer is good. All right, so how do you know all this? And that's what we're going to hear about in the class, is how does the perceptual system work, so we'll know which things will not kind of mislead it. And we're going to see zoos of techniques and kind of look at which ones are better for different tasks. So the dream system, if we wouldn't have this class anymore if we had the dream system. And the dream system is basically, we've got this giant catalog, right? It's a matrix of here's all the techniques that are available out there. Here's all the tasks that scientists ever want to do. And kind of here's a scoring for how well these things do. And you just look up the task and you put down, okay, this is the one that I should be using. It's the maximum there, and off I go. You'd feed it into the computer. It would do an optimization. Then we'd come back with the technique. So Chris Healy is actually working on this at NC State, and they've got a kind of visualization kind of what they call expert system that has some of this in there, and so you can ask it. It'll give you, here's a good example. Here's some other things you might try, but we don't have the data to fill out the table, right? We've got a few user studies that we're going to study, look at in the course, but like how's the best way to display tensor fields? That's wide open, right? You're going to have to kind of think about this yourself. And so for this semester, so this was the assisted visualization tool that I was talking about at NC State, and there are other people working on this as well. But for today, for this class, you're going to be the intelligence, and the artificial intelligence is going to be not artificial intelligence. I'm going to talk about what's known. I'm going to try to organize my presentations of 2D, scalar, 3D in terms of here's some questions, here's some techniques, here's which ones do well at that, to give you the start along a catalog. But you're going to quickly realize that some of the things I put in there are guesses, right? And some of the things that they're incomplete, right? And so you're going to be thinking, okay, I could also use this for this other task that wasn't even mentioned on the list. If there were two of me, one of me would have written the kind of online, continuously going scoreboard that was doing just this. The scientists would have questions, we'd auto-generate data sets, you could implement your technique as a VTK filter, you plug it in, it would ask people on Mechanical Turk, to try to solve the problem, it would have the leaderboard for each question. So, if you have $1 million and you want to spend it on something, pay somebody to go do that, make the world a better place. All right. So that is looking at kind of what are the characteristics of data, what are goals, and now we're going to, later in the course, see how those fit. We're going to completely change subjects now and look at a topic of putting props into visualization context. This lecture has the benefit, you don't have to know a lot of visual perception, you don't have to know a lot of techniques to understand it, so I just moved it from the end of the course before to the beginning of the course. So while you're reading up on your perception, we can think about, okay, here's what's going on. So one of my favorite examples of this, I have many favorite examples of this.
Disembodied.
It's one of my favorite things. So this is looking at, so Ken Hinckley at University of Virginia was working with Randy Pausch and physicians to do slicing, arbitrary slicing of CT scans to see what was going on inside of a brain, right? And so with the mouse, you can try to, and the physician would get lost. Where am I looking? Which direction is this slice? So they put a magnetic tracker inside a baby doll head so they could know which way you're holding it. And they put one inside on the plastic sheet, and you would put the plastic sheet on the baby doll head, and then the place where it sliced through is the view you had, right? And so you can see, it shows you kind of on a 3D rendering where the slice goes through, it matches the actual physical model, and then these are the images, and you can know what the context is. Now, the physicians would do this for about 10 seconds, but then they could put it down their lap, right? Because they could kinesthetically understand what they were doing. They still had the map in their head, and the whole screen can now be used for showing the data. And so it was kind of a very natural way to have a prop that was, here's the coordinate system you could understand and not have to be looking at, thinking about what was going on.
There's a really creepy doll head.
Creepy doll head, yeah. Disembodied heads are often, disturbing. All right. Another one of my favorite ones of these. I have many favorite ones of these. So this is Art Olson and Mike Peak at Scripps Research. So they use 3D printers to generate molecular surfaces, and then they also wanted to be able to see kind of the backbone going down inside, and so you've got kind of holes that are in the surface, and they squirted orange dye, and then they squirted, you know, green dye in there to label the insides. And so now you can kind of feel the backside of the molecule while you're looking at the front side and see what's going on. Here, we see the transparency is hard even in the real world, right? So it's not just because in the computer you do things transparent, you can't figure them out. It's also challenging to do with any transparent thing. All right, the next step was they had a $50 standing prize for anybody who could thread these kind of glowing things through the center of these holes. People tried, you know, blowing, you know, thin, you know, pushing fish line through to pull the string through. Finally, somebody got the prize. They threaded this thing through. So this is glowing thing going inside. The other thing that they've done is augmented reality, right? And so this is where you kind of have a see-through camera view of what you're looking at, but the computer can draw things on top of it. And now you've got the physical molecules, two of them that you can push together and see what the response is in the computer. And so we're going to actually see some of that in action. This is one of my all-time, I wish I had thought of this, ideas.
By combining the two emerging computer graphics technologies of autofabrication and augmented reality into a molecular modeling environment, we have created a novel and useful human interface to the complex world of structural molecular biology. Computer autofabrication technology, sometimes called solid or 3D printing, has evolved over the last decade from a rapid prototyping tool for product design and manufacture to a class of more broadly applied output devices used in many contexts where physical representations are helpful. All of these technologies utilize a layer-by-layer buildup of a physical part with some method of support for overhangs in the build direction. A number of different types of solid printers are on the market, utilizing materials ranging from starch to steel, and enabling the production of parts with various physical properties. Utilizing our component-based Python molecular viewer, we have produced monochrome models of ABS plastic and full-color models of starch and gypsum. With the easy autofabrication of such models, we can now test our hypothesis that the perception of the complex shapes and interactions of biological molecules can be enhanced by the manipulation of physical models. Designing in physical analogs such as magnets to represent the hydrogen bond complementarity of DNA base pairs provides additional manipulative input and output. By wrapping the widely disseminated AR toolkit into the Python environment, we've enabled the integration of the physical molecular models with the computer models used to generate them. Camera tracking of markers built into the models and video compositing of the computer-generated graphics provides a low-cost, transportable environment for enhancing the understanding of biomolecules for education and research. An interactive lesson on the identity and characteristics of the 20 different amino acids that comprise the protein alphabet has been generated for this environment and is being tested in an undergraduate biochemistry course at the University of Washington. More complex models of protein structure can be designed and printed. Here, a multi-component model of a protein's polypeptide backbone demonstrates the flexibility of the linear protein chain, and with embedded magnets, the propensities of the backbone peptide units to hydrogen bond to form higher-order, three-dimensional structure. These physical representations can then be used in the augmented reality environment to explore the chemical and spatial relationships between the amino acids as they interact from their positions along the protein backbone. Here, individual AR markers identify amino acid side chains that can be rotated around the bonds connecting them to the backbone. The system shown represents an interaction environment with 30 intuitively manipulated degrees of freedom. Since the side chains are only virtual, we can change their amino acid identity at will through the PY-ARTK interface to the molecular modeling environment. Thus, any of the 20 different amino acids can be placed and manipulated in this context. the PYARTK component enables the assignment of geometries, animations, and masks to the AR markers or sets of markers. Changes can be made interactively as the modeling proceeds. Computer graphic object, camera, clipping, and lighting controls are provided in the interface, as are the video tracking and composite display. Here we integrate the physical protein backbone of the HIV protease with computer graphic display of various protease inhibitor molecules that are effective in the treatment of AIDS. The drug molecules are shown by means of an animation player. Notice that a mask is superimposed on the physical backbone, providing correct occlusion of the computer graphic with the video texture. Finally, we show analysis of protein structure and function for the natural antioxidant protein superoxide dismutase, SOD for short. The animated electrostatic field vectors show the forces on the negatively charged oxygen free radical. The transfer function widget in the molecular viewer is used to interactively manipulate volume-rendered electrostatic potential. With this interface, we can manipulate interactions of two SOD proteins which form a dimeric complex and provide an intuitive way to guide computational exploration.
So it's not ridiculous to do this as part of the final project in class. We've got 6 degree of freedom trackers in the department. The AR toolkit is available for tracking things. There's a 3D printer in physics. There's one in the science library. There's one in art. But you better convince me that that was the right way to display it, right? And so it's really cool and awesome, and so it's got this really wonderful appeal, but the question is this the best way to answer this question? And for some of the training exercises, it clearly was. It's not the best thing for everything, but you know, again, outside the box. So I'm gonna, yeah, we'll go ahead and do this. This is a remapping. This is a quite interesting remapping.
Fail.
That's because my wireless is off and my network's not plugged in.
So that was that they did that in 2004. Have they
Yep.
updated that at all, or?
They have somewhat, yeah, but it was pretty darn good the way it was.
Yeah.
So, and Art Olson is a chemist, right? He's not a computer scientist, so he doesn't care if it uses the latest whatever. He's like, okay, this is what I needed to.
This rotating
to
3D
do.
model shows the same. Single cell, similar to the trillions of cells that make.
This is a more recent graduate from Art's group that was at, this is a Scripps Research Institute in La Jolla.
Of your body. This particular cell came from the pancreas of a mouse, and it's used as a biological model to study diabetes in humans. Fading the outer membrane unveils the cell's internal organs, called organelles. The round insulin-secreting vesicles, color-coded here in blue, dominate the interior, 12,128 of them in total. Fading these blue vesicles reveals a network of mitochondria, color-coded in green, sprawled about the yellow, color-coded nucleus. Scientists and general audiences alike can learn a great deal about biology by comparing internal structural differences between cells harvested from different environments, that is, from different parts of your body or from different life cycle stages. But even comparisons that seem obvious in a single model can deceive, let alone across multiple models. For example, approximately how much of the cell's total volume do you think that this yellow nucleus occupies? About 12%, 26%, or about 39%? How much of the cell's total volume do you think that the green mitochondria occupy? About 7%, 42%, or about 68%? Believe it or not, the correct answers are closest to 12% for the nucleus and only 7% for the mitochondria, much lower than most people infer by glancing directly at these representations of the data. A tool we've developed allows scientists and general audiences alike to compare and contrast multiple descriptive parameters of visually complicated 3D structures like this cell at a glance. By organizing the organelles and averaging their volumes, we can represent the cell as a simplified 3D graph that retains qualities of the native model. Here, a viewer gets a gut-level impression of the relative volumes of each of the organelles, far closer to the correct values, but they can still appreciate that this data represents information about a cell rather than something more mathematically abstracted.
Seriously?
The same tool enables us to rapidly compare otherwise similar-looking cells.
Seriously, that was ridiculous, or seriously, that's
That
ridiculously
was
great?
super cool. What is the
Okay.
gray thing?
Golgi,
The HOMA?
the Golgi.
Two cells on the
Modifies proteins.
Okay.
left, collected after glucose stimulation, are smaller and have a different organelle distribution than the two unstimulated cells on the right. This information is much easier to absorb by looking at the simplified cells on the bottom, rather than by mentally merging the information from the original models in the top row with the quantification information in the pie chart shown in the middle row.
All right.
Wow.
Wow.
That was really cool.
How did they convert it into that representation?
Yeah, go read the paper. All right.
Well, they have a 3D model of the whole thing, right? So
They very carefully vesicalized all those things. What they don't tell you is when you have the TM data set of that kind, it's like a year's worth of somebody's time, very carefully, slice by slice, picky. So if you make a huge impact in TEM microscopy, make an automatic segmenter that will do that. And
I'd have to know
everyone
what
will-
TEM stands for first.
Yep,
But
yep.
you're not going to tell me?
Transmission electron microscopy.
Okay.
So it's basically, in this case, it's thin slices in a scan, thin slice in a scan, thin slice in a scan. Yep. All right, so this is kind of a prop that is a flow line that goes through these granules, but then it kind of colors and makes opaque the ones that are near it, right? And so this is kind of dealing with the transparency versus opacity issue, drawing attention to the areas you care about, because it's showing you kind of what the surfaces are near these lines, and you can see through kind of the other things to more the back. It draws your attention to where you're going. It gives you a distance estimate based on color, right? So you don't have to do the visual estimate of the distance because the color map tells you closer or further from the lines. All right, this is a more traditional prop. And so this is basically a fluid simulation around a delta wing aircraft and a fighter jet. And if you don't have the fighter jet and the delta wing, you have to kind of infer which part of what thing is shedding this vortex. And just by putting the thing back in there, it helps you understand the context very much more clearly. This is mixing a theory plus data. So this is looking at acetylcholine receptor protein structure. I don't know what acetylcholine is, but I guess it's a name for protein receptor
It's a really
structure.
important one. Yeah.
The purple surface is the protein density of the scan. The blue surface is membrane density. And the orange cylinders are a theoretical helical bundle model for proteins. They say, this is what we think proteins bundle like. Here's the actual data model. Does this fit in that, right? And so here, you can mostly think of the scan as a prop in which to compare your theory, or a theory as a prop to say, okay, is this a reasonable explanation of the data that I'm seeing here? So it's comparing these two things in the same display. All right, there's a video that I'm not going to have time to show, but if you go to there should be a link in the PDF file that I sent you can go look at. I'm going to go through some of the different structures of superoxide dismutase. So this is the SOD molecule that they were holding up in the end of Art Olson's thing that was showing the electrostatic fields going into there. So superoxide so this is something that helps with antioxidation. This is an antioxidant. It takes the superoxide, it dismutases it, turns it back to an oxygen by dropping on a proton onto it. Yeah, don't.
So
Past
it's
my
an
level of
enzyme?
understanding. It's an enzyme that
Yeah.
that reduces free oxygen radicals in your blood. So these are all representations of the same molecule, right? And in some sense, a lot of molecular graphics is a prop, right? You're trying to understand what is the shape of this thing and what are the characteristics of this thing. And so this is looking at a ribbon representation of the backbone, which is kind of the primary structure sequence of the protein and how it wraps around in space. And then they've got a copper and a zinc molecule, atom inside here. And if I was a better chemist, I could tell you which of these was by their color. And then they're colored by which of the kind of regimes of the protein, the subunits of the protein they are. This is a surface model that's showing where a solvent could access it. So it's, you take a water molecule, you roll it all around outside the protein, and everywhere the water could get to is kind of the accessible surface of the protein. Again, colored according to subgroups. This is all of the atoms drawn as spheres, with I think their bonded radius shown. And so this gives you an idea of what's going on. And I think this is just the backbone. I don't think this has all the side chain atoms in there. You wouldn't be able to see through it. And then this is a surface colored according to, I think, partial charge. How much is it a positive or negative electrostatic charge, rather than according to group that you're in.
So what part of that is properly a prop?
So this, the atoms themselves are props. This is, the ribbons are props. This is more like a computed surface, right? This is more like an isosurface of the density. So this is more like a standard visualization, and these are more like props.
The top right is the space filling model, right?
This is the solid accessible surface.
Okay.
This and this are, would all be space filling. If this had all the atoms, it would be a space filling model as well. All right, so this is the surface drawn as kind of semi-transparent dots, or little, things vertical to the surface to give you an idea of which way it is, and colored by, I think, the type of amino acid that's near the surface, right? And so there's acidic, and there's basic, and there's hydrophobic, there's hydrophilic, and there's this is an abstract representation of the ribbon drawn as strokes on a kind of vector display, along with the kind of stick model showing you the bonds between the atoms. And this is the main chain. The backbone goes along the ribbon, and then the side chains come out off the sides, right? And there's different kinds of side chains coming out in different locations. And then these two kind of gnomons show you the two copper and zinc atoms and how they relate to the other atoms. So this one is very much empty space, and you can see what's going on. If you could rotate it and have stereo, you'd have a much better understanding of this depth, but in any case, you can see through a lot more.
What question does that picture answer?
This answers the question about which side chains are close to the copper and zinc and might be in there kind of coming in and dropping the proton onto it to do the enzymatic action.
I see.
So this is very similar to the one we saw in another video. It's the kind of, the kind of stick model together with vectors showing you which way the electric field gradient is going. And this came from a movie, and in the movie these are all flowing in towards, if I were a charged oxygen atom, where would I be pulled into, right? And so this field goes out far beyond the edge of the enzyme and captures the superoxide, brings it inside, it becomes uncharged, and then it kind of wanders back off, and it opens up and resets, and then comes a new oxygen. And there's two of these things back to back, and they're both going at the same time, so whichever way you come in, you kind of get reduced. I don't know if it's reduced. You get turned into a normal.
Redoxed.
Yeah. You're no longer superoxide.
Yeah.
Just oxide. All right. And so here's the references for the different things that I talked about. At the end of each of the slide sets are references for the things inside. In later years, as I insert things, I actually put the reference on the slide. It's a better way to do things. But when I started on, I just kind of put at the end where the references came from. All right. So now we're ready to study some perception. You're reading on some perception, and on Tuesday we'll get started with that.